everyone, and welcome to another episode of Eyes on Earth. Our podcast focuses on our ever-changing planet and on the people at EROS and across the globe who use remote sensing to monitor the health of Earth. My name is Jane Lawson, and I'll be hosting today's episode, where we're talking about how satellite imagery can help with disaster monitoring in near real time. A newly developed system using the Harmonized Landsat Sentinel-2 dataset and artificial intelligence was put to the test when Hurricane Ian tore through Florida in late September 2022. By comparing pre-storm and post-storm imagery, the system quickly flagged anomalies statewide, such as brightness, which could indicate exposed sand or bare land after a hurricane. Harmonized Landsat Sentinel-2 data is available through the Land Processes Distributed Active Archive Center, or LP DAAC for short, located at EROS. Our guest today is here to talk about the development of this new monitoring system. Zhu is an assistant professor at the University of Connecticut, where he serves as the founding director of the Global Environmental Remote Sensing Laboratory. He is also a member of the Landsat science team, and he previously worked as a land change scientist at EROS. Zhu, welcome to Eyes on Earth.
Thank you, Jane.
Let's first lay the groundwork for talking about Hurricane Ian by discussing your background a bit. At Boston University, before you came to EROS, you and Curtis Woodcock developed an algorithm that uses all available Landsat data to detect change and classification of land cover, called Continuous Change Detection and Classification, or CCDC. And that was published in 2014. What need did this algorithm and variations of it since fill in the remote sensing community?
One of the major needs I think this algorithm fill in is how to use this really dense time series. As we all know that Landsat data is open and free policy started. And after the cloud shadow detection getting into more mature phase, there are lots of observations available for the same location. And how to better use it? At that moment, I don't think that too many people have ever thought of this question before because there's never been so much data available at this high resolution. And CCDC actually, I think, is one of the first approach trying to linking all those dots together into a time series model. And using this model, we're able to not only capture what has been changed, but also to capture the seasonal and also the temporal information throughout the time series data set. And there are a lot of variation of this algorithm since it was published, and different kinds of application has been applied, for example, forest degradation, coastal tidal wetland change, and also recently has been used for even monitoring this nighttime light change at much larger scale. So I think that's mostly what has been done since 2004.
Excellent. So let's jump ahead in time now to almost today and tell us about the development of the University of Connecticut's Disturbance Watcher and that intended purpose.
So this is actually a very new development here at UConn. What we're trying to do is we're trying to make this watcher to monitor the entire United States on a sub-weekly basis. So every 2 or 3 days, we'll update this map at a high resolution, a 30-meter resolution for every land pixel in the U.S. And so far, we already finished multiple places, like in California, in northeast part of country, in Florida. We're also doing something in the Central Plain and other places. We're going to expand for the corners wide. But one of the first events we targeted is Hurricane Ian. And this watcher is not able to achieve this goal if there's no code algorithm, no SCCD. So SCCD is another more near real-time approach. It's adapted from the code, but it's called the stochastic continuous change detection algorithm, which is able to getting the data online in an online change detection approach, getting the data and then getting the results much faster than the code approach and achieving similar accuracy. And also another thing I want to emphasize is the availability of Harmonized Landsat Sentinel-2 datasets. That's a huge differences compared with what we can do versus now. Consider right now we have Landsat 8, Landsat 9, Sentinel-2A, 2B all together, we're able to get a 30-meter resolution data in less than 3 days. That's a big improvement in terms of the temporal frequency of those medium resolution data sets. And another thing I want to emphasize that this harmonized data set created actually by NASA, they are also making them in a more timely domain. Basically, previously, I think just a few months ago, we need to wait for like a week before the data is collected and we're able to get the data. Now it's only like less than 2 days when the data is collected and we're able to get this data set. So this greatly reduced the latency for this kind of near real-time monitoring system.
Do you want to tell us more specifically about the work with Hurricane Ian, the process and the results of using this disturbance watcher?
So this Hurricane Ian, we know it has causing a lots of devastating damage to the entire state of Florida. And even just before it's trying to touch the Florida, we know it's going to be a big event. We know it's the time is going to be the most important value for maps like that. So we actually prepared time series analysis, time series data for the Harmonized Landsat Sentinel-2 data sets before it's reaching the state of Florida. And when it's actually landed in Florida, we are just waiting for the first good image. And basically, when we get the first clear sky image, we put that image into the already analysis data, and the data actually can predict what the future date would be looks like based on the past. And when we get this first clear sky image, we are able to compare the predict with the observed, and then using the high performance computing center capability to provide this statewide hurricane damage map almost in near time.
Did everything go as you predicted, or did you learn anything new from this process?
One of the most important thing we learned through this process is that near real time is just not just about algorithm. There are a lot of moving parts. You have to figure them out, and you don't want to hear any kind of surprise. For example, the high-performance computer we use at University of Connecticut actually didn't work well. There have been some problem when the hurricane actually landed Florida. So we actually waited, I think, for a day or two, at least a day, to have the computer ready to be able to be used. So this is a latency we never expected when we write an algorithm, right? But in reality, we have to count every kinds of moving parts, and anything, if they are not right in its original expected condition, it's going to causing latency to your final results. And consider our map is trying to be used for the people who is, for those rescue, for damage. So any minutes, the earlier, the better, right? We want to just reduce this latency as much as possible. Right now, it's about 3 days, but 3 days just not good enough, right? And it's possible if the delay of the hardware is more than 5 days, then the map is not time relevant anymore. So that's something I want to say. Yeah, every moving parts, we need to making sure they're in the right place, in the right condition.
There's an urgency to this because you're trying to save lives and property.
Right.
How would you ultimately like to see this disturbance watcher used then? By what types of groups, for what kinds of disasters, and in what areas? You mentioned CONUS, so across the continental United States.
So this disturbance watcher, we want to build it for a generic purpose, not just for forest disturbance, not just for one type of disturbance type, for example, the hurricane. We want to do it for all. So for all kinds of land disturbance types, including landslides, earthquake, hurricane, and even some like flooding, and also some anthropogenic change like constructions, forest harvest, forest plantation, and stress, disease, fire. So we want to include everything in this disturbance watcher, and for all the land surface type. And the ideal hope is that we can expand this CONUS-wide And we can also extend to Alaska if we want, and to provide this useful information. And have you ever used application called I think the earthquake monitor by the USGS? Basically, if you feel like something, it looks like earthquake, you go to that website. And this is something we want to provide. If something happened, if some disaster, some kind of disturbance happened nearby you or in any parts of the US you're interested, this is website you're going to look for.
That seems incredibly useful. How does the Disturbance Watcher then fit in with your area of study as a member of the Landsat science team? So your area of study is toward near real-time monitoring and characterization of Landsat surface change for the conterminous US.
So you already mentioned the two components, major component in this team work. First one is the monitoring, near real-time monitoring. Second one is characterization. And this near real-time actually fill in this monitoring component. So anything happen on the land surface, we want to see that. We want to identify that in a near real-time mode. And we also have another component to actually characterizing, like what's the land cover before and after, what's the agent or the driver of this disturbance. That's another work. We're also working on that, and hopefully there's publication on that for corners-wide characterization of this land disturbance for the past 30 or 40 years.
As someone who has worked with the Landsat archive on land change, including the Land Change Monitoring Assessment and Projection, or LCMAP program, during a stint at EROS, and also forest and coastal wetland research, can you describe your perspective of the significance of the Landsat program?
It's so important. I think one of the most important thing is it's open and free. Without that, I don't think any work from the LCMAP or the coastal tidal wetland we're doing is possible. And another thing I think is extremely important is this analysis-ready data. So for a long time, I still remember when I was a student at the Boston University, I spent a few weeks to download 500 image. You have to click twice for one image. And then I spent 1 month to install atmospheric correction algorithm and run the algorithm to get surface reflectance and run the F-mask to get the cloud shadow snow detection. So just get the data ready for you to do the analysis. Can take you several months for one pattern row. But what EROS has created is analysis-ready data, entirely changing the game. We can just download data and do the analysis. It's a big thing. And another significance of this Landsat program is almost, if you look at the literature, almost every important major medium resolution, global or large scale work, you can see Landsat showing up. Sometimes you can see Sentinel-2, but a lot of time you're going to see Landsat along with Sentinel-2 or just Landsat, because it's the only data set that cover global scale at medium resolution and has 50 years of time from Landsat 1 all the way to the current Landsat 9. I just attended Picora 2020 and we celebrate the 50 years anniversary for Landsat program, and it's a huge success, I would say. If you rank Landsat as the second Earth observation satellite, I don't think there's another satellite can rank the first. It just has too much huge impacts on Earth observation, and I'm so glad it's this continuity, and also Landsat next is going to continue its success and getting more exciting and even more frequent, more higher spectral, and high resolution data set. Landsat is going to not only a long-term success, but also the future for remote sensing.
Thank you for sharing that perspective. Do you want to share any notable memories of your time at EROS or any connections or experiences here that have remained important to you?
Sure. There are a lot of connections at EROS, and a lot of people, when I talk about, I may cry sometimes, like Tom Laughlin. He's the person who got me into EROS, and I worked with him. Such a nice person. It's like the academic father of me, always carrying my research and also give me the great vision for this, for my research. And there are a lot of other people I want to mention, like Jess Brown, Heather, Changzhou, Su Mingjing, George Shen. There's so many people there. And if I want to give all the name, I'm not even finish within like 15 minutes. But all those people, I still keep very close connections. And we are still working closely on papers, project on the LCMAP, on the NLCD, on the urban detection, on deep learning, machine learning method. I think EROS is a big Earth observation research hub, and lots of exciting research is going on here at EROS. And I just feel like I'm so fortunate to have worked at EROS for 2 years and know all those great people there. It's my great opportunity and honor to be able to have the 2 years there.
Thank you for sharing that. Is there anything else you'd like to add today?
I think just wait for our product. The near real-time monitoring capability is going to be available for the corners-wide, hopefully at the end of this year. So it should be soon. We're going to have actually corners-wide product available end of this year or early next year. So if you have any kind of disturbance, you can go to that product. Another thing is that we already have a corners-wide disturbance characterization platform. Basically tell you all the disturbance happened in the past 35 years, 60 years, from 1985 to 2020. So not only tell you it has been disturbed, but also tell you the agent of the disturbance is mechanical, it's fires, agriculture, it's forest, it's stress, it's construction. So a lot of categories you're able to see.
And is there a name for the disturbance product that shows change over time?
We haven't get a name for the system yet. But if you go to my website, JERS Lab, there's a product on the upper right. And if you see the multiple image, if you click those image, you're able to see this platform. We put all the platform in the products link there.
Great. And we'll be watching for the CONUS Disturbance Watcher.
Sure.
Thank you, Zhu, for joining us for this episode of Eyes on Earth, where we talked about satellite monitoring of natural disasters. And thank you to the listeners. Check out our EROS Facebook and Twitter pages to watch for our newest episodes. And you can also subscribe to us on Apple Podcasts and Google Podcasts.
This podcast
is a product of the U.S. Geological Survey, Department of Interior.